All right, so here's another example, and this is a pretty long one, so you should try to write small, make it all fit. I have a vertical spring, a force constant 800. That's the spring coefficient, K, put it right there, 800. And it is attached, so the spring is vertical, but it's attached to a horizontal surface as shown below. So this is just describing the picture. There's a 10 kilogram block that is placed on top of the spring, just as shown. And then it's allowed to descend slowly, compressing the spring until it reaches equilibrium. Allowed to descend slowly means that you're not going to just drop or like put the spring block here and release and let it fall, because if you do that, it's going to fall past the equilibrium point and it's going to start oscillating like this. Okay, so what you do is you put the block on top and you kind of hold on to the block and let it slowly fall. It's like a controlled fall so that it doesn't oscillate. Cool. So that's how that works. It's different from the other example where it was a sort of an uncontrolled fall. It just hit the thing and it went all the way back down, and then it would shoot the block back up. Here it's a controlled fall, which means that it will go down until it reaches equilibrium. So it's going to start over here at point A, and it's going to slowly descend until it reaches equilibrium at point B. So point B is equilibrium. Okay, and the first question is, what is the spring's compression X at equilibrium XB? So what is this compression here, XB? Okay, then the block is going to be pulled down an additional 30 centimeters. So you're going to pull the block down an additional 30 centimeters. So this is 0.3 meters. And then it's released from rest. When it's released from rest, what's going to happen, just as a overview real quick, is you're going to release it from here with an initial velocity of 0, which is the same thing as VC equals 0. And it's going to go back to B, cross A, and then go up a little bit more. Okay? And the problems here, parts B, C, and D are asking, what is the block's maximum speed and where does that happen? I'll talk about that soon. What is the block speed once it's back to its original height? The original height is here. And if I want to know the speed here, I want to know what is VA. And then what is the block's maximum height? Maximum height's over here. I already have A, B, and C. So, and then we're going to come back C, B, and A. And I'm going to call this D just because A, B, and C are taken. So I want to know what is this height right here, HD. Now notice that we want the height above the spring's original height. So I want to know HD from A, not HD all the way from the bottom. Cool, so it's a little bit different. All right, so let's first look for XB. So I hope you remember what's special at equilibrium. When you have a spring, a vertical spring at equilibrium, the forces are canceling. That's the definition of equilibrium. So at equilibrium, sum of all forces equals 0, which means the two forces will cancel. The two forces in the mass are, the whole time mg is obviously pulling this thing down, and because the spring is being compressed down, it pushes the block back up with a force called, with a force of spring, which equals kx. At equilibrium, these forces cancel. That's the definition of equilibrium, which means that they will be the same magnitude. And I can write kx equals mg. I hope you remember this, equilibrium in a vertical spring, kx equals mg. So when I'm doing part A and I want to know what is xb, this is how I'm going to start. kxb equals mg, because it's at equilibrium. B is at equilibrium. So xb is just mg divided by k, mass, gravity, I'm going to use 10, k is 800. xb therefore is 0.125 meters. That's the first answer. I'm going to put it right here. 0.125 meters is my xb. Let's go to part B, and I want to make a little, let's make a little separation here for these questions. For part B, I want to know what is the block's maximum speed and where does it happen. Okay, so the block starts at point C right here. I pull this thing all the way down at point C and I release. Now it's going to start going up. It's going to start accelerating up, so its velocity is getting faster and faster and faster. And the reason why the velocity is getting faster is because at point C, the kx is much bigger than the mg. Let's draw a little tiny mg. right? So if you're pushing the spring down, the spring's really pissed off and it's pushing back up. So this thing will accelerate up. The problem is once you cross your equilibrium, right? Equilibrium is right here. So at this point, you're being accelerated up. Once you cross your equilibrium, the forces are the same. Your kx is no longer greater, it's actually equal. And once you go above equilibrium, your kx is basically getting weaker and weaker and weaker. So the force that pushes you up keeps getting weaker once you cross, keeps getting weaker, and it's weaker than the weight force once you cross point B, okay? So you have an acceleration up, but then you go to equilibrium, which is 0, and then you actually start accelerating down, which means you start slowing down. So the fastest you will ever be is at when you cross the equilibrium. So I want you to remember that, and I'm going to actually write that down here. This is for the other part of the problem, but Vmax happens at equilibrium, okay? Please remember that on a vertical spring, Vmax happens at equilibrium. So when I ask you for Vmax, what I'm really asking in this particular case is VB, which is at equilibrium. Now I have a spring moving from C to B, and if I want to know the velocity of a moving spring on a vertical spring like this, we're going to use energy, right? And if it was a horizontal spring, it would be the same thing. But when you have a moving block spring and you want to find out some information, you use energy, okay? We're going from C to B, so I'm going to write KC, UC, work non-conservative, KB, UB. It might seem weird, and it is unusual that we're going from C to B. Usually you go A, B, and C, but now we're going back C, B, and A, right? So there's no kinetic energy at point C because there's no speed. Potential energy, there are two types. I have UC, gravitational, and I have UC, elastic. Is there a gravitational potential energy? I want you to try to get these because identifying this is the most important part. So is there gravitational potential energy? Hopefully you said no because there's no height. Is there elastic potential energy? By the way, I wrote UGEL. It's UCEL, potential energy at point C. There is elastic potential energy because the spring is compressed, right? So I have this because the spring is compressed. There's no work because once I push down, I do work, right? When I push down, I do work, but then I release and this thing is moving on its own. So from B to C, I'm not doing anything. I did some stuff before, but it doesn't matter. It doesn't matter on this question here. So there's no work non-conservative. There's also no friction, right? So there's no, both types of non-conservative work don't exist. Kinetic energy at point B, there is a velocity at point B. You're accelerating. In fact, it's the highest speed. So this exists. And again, here, there could be two types. There's UBG and UBEL. Is there gravitational potential energy at point B? Yes, because it's not your lowest point. Is there elastic potential energy at point B? Yes, because it's not the original length of the spring. Even though you're equilibrium, it doesn't mean that you have no compression. You've compressed down a bit. In fact, you compressed down 0.125. So now all we have to do is replace all these numbers and we'll be good. So over here I have half K, which is 800, and then X squared. The compression at point C, I hope you see right here. The compression at point C is the entire compression, which is 0.425. This is half M. I can plug in the mass. The mass is 10 VB squared. This is gravitational potential energy, which is M10 G10. What is the height at point B? If this is your 0, the height at point B is just 0.3, right? Hope you see that. And I'm going to put this other guy over here, running out of space there. Half K X squared. What is the compression of the spring at point B? Look at the diagram and tell me what the compression of the spring at point B is. So hopefully you said it is 0.125, right? This is the compression. So the height is this, but the compression is this. The height is relative to the bottom, and the compression is relative to the original length, right? So those are distinct numbers. Cool. So now if you notice, we have a bunch of numbers, and VB is the only variable. So the physics is done. We just have to solve here using algebra. And in the interest of time here, you should definitely practice this and make sure that you get the answer right. But in the interest of time, I'm going to skip some steps here and tell you that VB comes out to be, where do I have it? I wrote this down, 2.68 meters per second. And that is your maximum speed. All right, so let's go to part C. Part C is to find the velocity when you're back to your original height. Your original height is right here. So we want to know what is the velocity at A. So for part C, we want to know what is the velocity at point A. Again, moving spring. So we're going moving block and spring. So we're going to use energy. I could use energy from C to A, or from B to A, whichever you prefer. C to A is easier because there are less types of energies here. The total energy is conserved, but there are less types of energies from C because there's no kinetic energy. B has kinetic energy, it has potential energy. B's are just a huge mess. So it's easier to go from C to A. So KC, UC, work non-conservative, KA, UA. Is there a kinetic energy at point C? No. What about potential energy at point C? Potential gravitational, potential elastic. Is there gravitational at point C? No, because there's no height. Is there elastic? Yes, because there's spring compression. There's no work non-conservative because once you release, you're not doing anything, and there's no friction. Kinetic energy at point A, the object is moving, right? So it's going to come back and shoot past point A. So there is kinetic energy at point A. And there is potential energy at point A. Now, is that gravitational? Is that elastic? Or is it both? Is there gravitational potential energy at point A? I hope you say yes, because there's a height. Is there gravitational elastic potential energy at point A? I hope you say no, because the spring is back to its original height. Back to its original height means that it is back to being uncompressed. Those are the types of energies. What is UC? UC is half K, K is 100, and then X squared. X is the compression of the spring at point C. Look at the diagram and see if you can figure out what's the compression at point C. The compression at point C is the addition of these two numbers, just like before. So 0.425. Over here I have half, the mass is 10. VA is what I'm looking for. And here, gravitational potential energy, M10, G10, H. Let's figure that out. What is the height at point A? Look at the diagram. I hope you agree. Hope you said that the height at point A is 0.425. The height at point A is the same as the compression at point C, and that should make sense. All the way at the bottom, you're fully compressed. All the way at the top, you have no compression at all. You have all height. So here, all height, no compression. Here, all compression, no height. They essentially swap. If you look here, you have everything you need except and only one unknown, so you can solve this. Again, in the interest of time, I'm going to skip out the algebra here. That part is done with the physics. So if you did all this, you get that VA equals 2.44 meters per second. Now, one way that you can tell that this answer is probably correct, one way that you can have a little bit more certainty around this answer is the fact that this number came out to be less than your Vmax. Down here, Vmax is 268. This is less than your Vmax, which is good. I put a little good check mark there. If you got a bigger number, then something's wrong because the 2.68 was supposed to be your bigger number. So that's kind of good. Let's go to part D and we'll make it fit right there. So what is the maximum height above the original height? So we're going from A to D, and I want to know not the height from the bottom, I want to know the height from the top of A. The height from the top of A. So I want to know what is HD, and the height at A, since it's the lowest point, we'll just call that 0. Okay? So it's an energy equation from A to D, right, on the way back. A to D on the way back, and we want to know what is HD. So KA, UA, work non-conservative, KD, UD. This is the easiest part of the question. There is kinetic energy at point A because you're passing with a velocity. There's no potential energy at point A. That's because we're saying that that's the lowest point between A and D, so the height's 0, and the spring is not compressed at that point. Work non-conservative is also 0 because we're not doing anything, no friction. There is no kinetic energy at point D because it's the highest point, so it stops. And at point D, there's only gravitational potential energy. We have a height, so we have gravitational, but we have no spring compression. The spring's already, the block's already off the spring, so there is no elastic. Okay, so the only thing you have is all speed at the bottom and all height at the end. So I have Ka equals U gravitational D. So this is half mv squared mgh d. The masses cancel, and then hd is Va squared over 2g. And Va is 2.44 squared divided by 210. I actually didn't calculate this number in advance. Just a second. But it should be 0.295. I could be off by a little bit. You can do this on your calculator. Again, the most important part was getting right before this point here. If you got here, then it's just a matter of plugging into the calculator. Cool. So that's it. We got all the answers. This question is really long. You probably wouldn't get something this long in a test. Even if you had a long answer, it's too many parts. But you could get 2 or 3 of these. And what I wanted to do with this example and the previous example is cover just about every possibility, every reasonable possibility you can have. Your professor can always do some crazy stuff, but this covers the vast majority of it. Okay? So hopefully it makes sense. Let me know if you have any questions.